Today we are pleased to have as our speaker Romain Maccary, who is a PhD student from the University of Ferrara, working with Professor Cristiano Guidorzi. The talk will be given on the complexity of gamma ray bursts and evidence for self-organized criticality. Romain, please go ahead. The stage is yours.
Thank you, Anastasia. Okay, so let me share my screen. Okay. So hello everyone. So thank you, Anastasia. Thank you to the Hermes collaboration to give me the opportunity to do this talk. So today I will talk about how the concept of self-organized criticality can help us to understand the burst emission coming from gamma ray burst. So a gamma ray burst is a bright, short-lived gamma ray flashes. They are the most powerful explosions that can happen on a stellar scale, and the amount of energy released by these events can be comparable to consuming a solar mass in just a few seconds. So as of today, there are two kinds of progenitors that are known to produce these bursts. So depending on their duration, so long duration gamma ray bursts usually come from the collapse of some kind of massive star, while short duration gamma ray bursts usually come from the merger of two compact objects, so either two neutron star or a neutron star and a black hole. So the object that is produced from this burst, from these catastrophic events, and that is ultimately responsible for the burst, could be either a stellar mass black hole surrounded by a thick accretion disk that is accreting matter at a very fast rate, or it could be alternatively a highly spinning neutron star with a huge magnetic field, a so-called millisecond magnetar. In any case, a relativistic jet is produced, and as it propagates, part of its energy is converted into gamma ray radiation by some internal dissipation mechanism, and the part that is the emission that is emitted during this phase is what we call the gamma ray burst. So from a time series point of view, a gamma ray burst is an incredibly complicated signal. It's a nonlinear, transient, non-stationary signal, and its shape, it's completely unpredictable. So a gamma ray burst could be made of just one or few smooth pulses, or it could be also made of several tens of pulses that sometimes are also overlapping. So an important question is, where does this diversity come from, and what this diversity is telling us about the inner engine activity and about the dissipation mechanism? So gamma ray burst time profiles present flux variation on different time scales, so ranging from tens of seconds to a few milliseconds for the more variable ones. And if one wants to study how these time scales distribute, how these power distribute among these time scale, one can compute the so-called Fourier transform of the signal, and then one can compute the power density spectrum, or in short, PDS. And so gamma ray burst PDS were studied either on individual gamma ray burst time profiles, or also computed on average ensemble of different gamma ray burst time profiles. And it has been shown that usually the gamma ray burst PDS decays with a frequency according to a power law, with an index that typically ranges from 1 to 3. And as we will see in a few moments, this kind of power law PDS is also, we can also find it in a totally different context. So gamma ray burst does not generally produce a steady, continuous emission of radiation, but it's rather constituted of different intermittent episodes of intense activity that are separated by some episodes of inactivity. So if one wants to study this intermittency, one can compute the so-called waiting time, which is time elapsed between two successive events, and waiting time of gamma ray observed during gamma ray burst prompt emission, or observed during the later X-ray flares, were computed, and waiting time were it has been shown that waiting time distribution can follow a power law distribution with a value of the exponent that is near to the value of 2. And again, such power law weighting type distribution are observed also in totally different astrophysical phenomena, as for instance, solar flares, that we'll also see in a few moments. So the hypothesis that the diversity observed in gamma ray burst light curves could be just the result of different random realization of the same stochastic process, which is working near to a critical regime. This hypothesis has been put forward by two scientists in 1996, Stern and Svensson, and in their work they proposed a stochastic process, which is the so-called stochastic pulse avalanche model, in which is able to reproduce accurately the light curves. And this model was so this model is working near to a critical regime, and it was recently optimized by using a genetic algorithm. And now the new version of this model is able to very precisely reproduce the gamma ray burst diversity. So what is self-organized criticality? So self-organized criticality, it's a model that was introduced in the early 80s to explain the occurrence of power law power density spectra in some dynamical systems. So it's very similar to gamma burst, in which we also observe this kind of PDS. So this system, owing to some driving force, they are able to spontaneously reach a critical point. And above this critical point, they are unstable, and so they will release their energy through avalanches. So avalanches are intermittent, nonlinear, and similar release of energy. So why could these systems, so why could self-organized criticality be relevant for the study of gamma ray bursts? So first of all, as I said, systems governed by SOC present power law power density spectrum as gamma ray bursts do. Also, the weighting time distribution of such systems is often power law distributed as gamma ray bursts. And finally, often this system will observe an avalanche mechanism in the way the energy is released. It is released according to an avalanche mechanism, which is similar to the pulse avalanche model that I just presented in the previous slide. So self-organized criticality was initially illustrated by the example of a sand pile into which some sand grains are dropped on the top of the sand pile. So as the sand pile slope, as sand piles are added to as sand grains, as sand grains are added to the sand pile slope will grow until eventually it reaches some critical threshold above which the mechanical equilibrium cannot be sustained. And so above this threshold, we observe avalanches. And as other sand grains are added, the process will repeat. So whenever the threshold is exceeded by the system will produce avalanches to restore the equilibrium. So self-organized criticality it's made of two fundamental concepts, self-organization and criticality. So self-organization means that the system is not controlled at all by some external parameter, like you can think about the temperature in some phase transitions. Here, the system is not controlled by a parameter, but rather evolves freely towards a more organized state. And criticality means that the system will oscillate between a stable state and an unstable state, and will release energy in the form of avalanches whenever some instability threshold is exceeded. And it's very important to note that the avalanche size distributions of these events are described by power law functions. So it's a fundamental property indeed, the properties of the single shots occurring during these avalanches. So by this I mean the duration of one avalanche, or the energy released by one avalanche, or the flux emitted, and so on and so forth. All these quantities are described by power law distributions. And the self-organized criticality theory is also able to predict the values of these exponents. And so in the simplest version of self-organized criticality, these exponents only depend on one parameter, which is the S parameter, so often called S, it's a dimension of the space in which the energy is released. So for example, if this parameter is equal to 1, it means that the energy will be released in only one direction. If it's equal to 2, it means that the energy will be released in a plane. And finally, if S is equal to 3, it means that the energy can be released in a volume. So self-organized criticality has already achieved significant successes in astrophysics, being invoked to explain a wide range of astrophysical phenomena, starting from local events in our solar systems like the lunar craters, the shape of Saturn's ring, and also solar flares, going to extragalactic events like the flares from magnetars or the flare from blazars, or even more recently gamma ray burst. So in the case of solar flares, these kinds of studies are going on for a while, and so the accumulated statistics is now excellent, and the experimental results are in very good agreement with SOC predictions. For gamma ray bursts, instead, self-organized criticality has entered in this field a bit more recently with the study of gamma ray burst X-ray flares, which are the last shots fired by the central engine. And so in this case, experimental results and prediction from the SOC theory could be in agreement, provided that the S parameter is equal to 1, which is slightly different from solar flare, where this parameter has to be equal to 3 to match the prediction of SOC theory. And finally, for gamma ray burst prompt emission, so recently some studies claim that the distribution, the observed distribution of the energy, for example, could be compatible with SOC prediction, provided that S is equal to 3. So in this case, just like solar flares. So the question is gamma ray burst prompt emission compatible with self-organized criticality? So as I just said, some papers already claim the existence of some evidence of self-organized criticality in gamma ray burst prompt emission, but these kind of studies lack two things. Essentially, they lack a good gamma ray burst sample with accurate, reliable redshift measurements, and most of all, they lack an assessment of the impact of the section effects. So in our work, we have selected gamma ray bursts with reliable, so by this I mean spectroscopic redshift, and we carried out studies to assess the impact of the selection effects. So for that matter, we used gamma ray bursts detected by the gamma ray burst monitor on board of the Fermi Space Telescope. So the Fermi Space Telescope was launched in 2008, and it's made of two main instruments: the Large Area Telescope, which is a pair production telescope, which is sensitive to very high energy photons from 20 MeV to 300 GeV, and the gamma ray burst monitor, which is a scintillation-based detector, which is sensitive to soft gamma ray radiation. So the gamma ray burst monitor, it's an all sky monitor, so it's made of it's able to see the whole sky unocculted by the Earth, and it's made of 12 NRI detectors, which are sensitive to soft gamma ray radiation from 8 to 1000 keV, plus two extra BGO detectors, which are sensitive to higher energies, so from 200 keV to 40 MeV. Okay, so in our sample, we have selected type 2 gamma ray bursts. So by this, I mean gamma ray bursts which are originating from a collapsar, so the collapse of some massive star. So to do that, we have selected gamma ray burst, long duration gamma ray burst, but we have also excluded the known cases of long duration merger candidates, as for example 21, 12, 11A, but we have also excluded, for example, 23, 03, 07A. And we have considered gamma ray burst with an associated spectroscopic redshift measurement. And so we ended up with 142 gamma ray bursts, both detected by Fermi GBM and with spectroscopic redshift. So we started by subtracting the background. So we applied the standard procedure of selecting two temporal intervals, one before the burst and one after the burst, and we have interpolated the background in the gamma ray burst interval. And to assess the quality of this interpolation, we had a look at the residual distribution. And after having subtracted the background, we have identified all the pulses present all the peaks present in our Loic curve. So to do that, we have used a peak detection algorithm that is called MEPSA, which is perfectly suited for this task. So MEPSA basically scan the light curve at different time resolutions, looking for some excess patterns to detect all the pulses present in the light curves. So then, after having identified all these pulses, we had to model them by using some pulse model. So we used the so-called Norris pulse model, which is a model that contains 5 parameters. So the first 3 parameters describe the pulse maximum time, the pulse rise time, and the pulse amplitude. So they are given by, these parameters are given by T0, tau r, and A, respectively. And the last 2 parameters describe the pulse shape and the ratio between the decay and the rise time. So the pulse shape is governed by the new parameter, which is intermediate between an exponential function if nu equal to 1 and a Gaussian function if nu equal to 2. And finally, the last parameter is the Xi parameter, and it governs the ratio between decay and rise time. And typically, it ranges between 2 and 4. So how can we compute the energy released by each pulse, which is the aim of our analysis, to find a distribution of the energy released by each pulse. So we started by, so first of all, we have computed to compute the energy, we have computed the counts. So the counts were computed by integrated the pulse model over the duration of the pulse. So by doing this, we have computed the integrated counts that are given by C to the Ci. And then we have computed the so-called conversion factor, which is given by the ratio between the fluence, the time average fluence integrated on the whole duration of the gamma ray burst, divided by the corresponding counts integrating on the exact temporal duration. And by multiplying these 2 quantities together, we obtain the fluence of a given pulse. And finally, to obtain the energy, we have multiplied the fluence by some factor, which is accounting for the distance of the gamma ray burst source. So we were able to compute the energy distribution of each pulse, and then we had to model this distribution by using some models. So we have considered either a simple power law model or a broken power law model, but really fastly we saw that a broken power law model is preferred because we clearly see a break in this distribution. But we had to ask ourselves, why is it so? Is this break only due to experimental selection effects, or is it also due to more fundamental reasons? So to answer this question, we had to understand and to model the selection effects that are present in our analysis. So the further away you go, you look into the universe, the brighter some gamma ray burst has to be detected by some instruments. So this means that the faintest gamma ray burst cannot be seen at large distances. So this effect is often referred to as a selection effect, or it can also be called sometimes Malmquist bias. And if you take a gamma ray burst population with a huge span of distances in this population, it means that at large distances, only the brightest gamma ray burst can be detected. And this implies that the energy distribution that you observe is not really accounting for the true way the energy is distributed among these bursts. So a possible strategy to tackle this problem is to divide the sample into bins of redshift and to study them individually. And so the first thing to do is to compute the detection efficiency in each of these redshift bins. So the detection efficiency, it's the probability to detect some gamma ray burst, and we have computed it first as a function of the pulse counts and then as a function of the energy of the burst. So we started by computing the detection efficiency as a function of pulse counts by performing simulations. So to do that, we have simulated some bursts with a very simple pulse shape given by the Norris function with some number of counts, so with a given number of counts. And then we applied MEPSA a certain amount of times to compute the amount of time MEPSA was detecting this burst. And the amount of time MEPSA detected this burst give us the detection efficiency as a function of counts. And then we have translated this detection efficiency as a function of counts into detection efficiency as a function of the energy by using the classical relation that we have between the energies and the counts once the distance of the gamma ray burst is known. So we have computed the detection efficiency for each gamma ray burst inside our sample, and then we have averaged this detection efficiency over all the gamma ray bursts that were present in our sample to obtain individual detection efficiency for each redshift bin. So now that we have computed the detection efficiency, we are now able to model the selection effects. So to do that, we started by assuming a given shape for the theoretical energy distribution. So here, for example, we have assumed that the theoretical shape is a power law. So the blue points here are drawn from a power law probability density function. Then, as I said, we were able to compute the detection efficiency, so the probability to detect a given burst in function of its energy. And now we are able to simulate the detection process. So we have simulated the detection process by performing so-called Bernoulli trials. So these trials consist into the following. So we select some burst inside our blue distribution, so some point in our blue distribution with some energy E, and we compute the detection efficiency, so the probability of detecting it. And then we draw a random number from a uniform distribution between 0 and 1. And then if this number is smaller than the probability of detecting this burst, then we say that this burst is considered to be accepted. And otherwise, if this value is bigger than the probability, then we reject this burst. So this burst is not detected. So by doing this, we are mimicking the detection process. And so if you apply this process to all the points inside our blue distribution, you obtain the orange distribution, which is the distribution of the detected pulses. And you can see that the selection effects are the difference between the blue and the orange distributions. And you can see that these effects become more and more important as you go to lower energy values. And then we have replicated this analysis to every bins of redshift inside our sample. And by doing this, we were able to compute to merge all the results together, and by doing this, to compute the distribution of detected pulses. And this distribution can be compared accurately with the observed distribution. So now that we have modeled the selection effects, we are able to model accurately the data. So we started by so as before, we started by simulating by assuming a given shape for the true energy distribution. So here, instead of assuming a simple power law, we have assumed a broken power law. And then we have simulated the detection process, and by doing this, we obtain the distribution of detected pulses as before. And now we are able to compare it with the observed distribution, and we are able to obtain the values that best fit the data. And as you can see, even after having accounted for the selection effects, a broken power law model still gives a better description of the data than a simple power law model. So here in this figure, you can see our results for the 4 distributions that we have considered in our work. So in addition from the energy distribution, we have also computed the luminosity distribution and the duration distribution and the waiting time distribution. So as you can see, these distributions are fitted with power law functions plus either a break or some flattening at low values. And in this figure, you can see our result for the power law distribution exponents for the 4 distributions that we have considered in our work, so energy, luminosity, duration, and waiting times. And in the top panel, you can see the best fit values with the associated error bars. And in the bottom panel, you can see how our values compare with other values coming from other works in the literature. And the dashed and the dotted lines represent the prediction of SOC theory for either S equal to 3 or S equal to 1. So overall, as you can see, our values are globally compatible with SOC prediction, but we noted that we saw some broken power law instead of simple power law, and this cannot be totally attributed to the selection effects. So now, while self-organized criticality is useful to describe the data, now it does not provide much physical insight. However, some physical phenomena as turbulence and magnetic reconnection can result into a self-organized critical state. So turbulence manifests as random chaotic flows in which some eddies of various scales can form, and in a turbulent flow, large eddies dissipate into smaller ones, and the observed energy spectrum in some range is also given by a power law. Magnetic reconnection, instead, it's a way to convert the energy that is stored magnetic energy that is stored in some magnetized plasma into heat, accelerated particle, and hence then radiation. So while the simplest model of magnetic reconnection, it provides a much slower reconnection rate than the one that we observe in astrophysics, turbulence may enhance the reconnection rate, making magnetic reconnection a credible scenario for emission of radiation from astrophysical relativistic jets. So indeed, turbulence can make happen the reconnection at a smaller scale than the steady state case of magnetic reconnection, and this could trigger an avalanche of small magnetic reconnection events. So finally, the last question is there some gamma ray burst emission model that produce avalanches similar to the one that we saw with self-organized criticality? So this is still an open question, but some already existing models, gamma ray burst emission model, could provide the beginning of an answer. So one of them is so-called Hickmark model, in which two mildly magnetized shells collide and shocked, and these shocks disrupt the initially ordered magnetic field lines, and then turbulence can set in, and this turbulence will further distort these magnetic field lines, and this goes on until eventually the magnetic field lines become so distorted that the condition for fast magnetic reconnection to happen is reached, and so above this threshold, a cascade or an avalanche of magnetic reconnection events can happen and produce the gamma ray burst. So as you can see, this model, this Hickmark model, shares a lot of similarities with self-organized criticality, and it contains the key ingredients of it. So, for example, a driver that is bringing the system toward a critical point, some instability threshold, and some avalanche mechanism that is able to release the energy. So to conclude, SOC, self-organized criticality, it's a model that is able to describe the dynamics of some dynamical system that spontaneously reach a critical point. And we saw that, so our work shows that there is evidence for self-organized criticality in gamma ray burst prompt emission, and our work was the first that was properly taking into account selection effects in this kind of study. But we have to note that we also observe some deviation to self-organized criticality, so especially the presence of breaks inside our distribution. And finally, we saw that some theoretical gamma ray burst emission model, like the Hickmark model, already contains key ingredient of self-organized criticality, as for example, an instability threshold and avalanche mechanism. Okay, that's all. Thank you for your attention, and you can find our paper by using this link or by using the QR code. Thank you for your attention. I'm happy to take questions.
Thank you very much, Romain, for a very interesting talk, a really good introduction to the self-organized criticality principles, and also for providing a lot of details on the procedure, really important details. Does anybody have questions?
Hi, Romain. Very nice talk.
Thank you.
I do have a question.
Yeah.
Most likely you already answered, but just curious. At some point, you mentioned that the simplicity of the model or the technique that you're using to reproduce the light curves somehow affects your results. To which degree is that the case, and do you have any way to improve
What do you mean by reproducing the light curve?
Well, you at some point you showed
when
that
we are modeling the light curve by pulses.
Yes,
You
yes.
mean, yeah. So the
Just
pulse model
wondering
can
whether
so the pulse model can affect the results, and actually we used a different we used two pulse models to check if it was if the pulse model was really affecting the result. But we also in our paper we checked that it was not really affected. So the conclusions are not affected. So maybe the values of the parameters of the power law distribution exponents can depend a bit of the pulse model, but not so much as I mean the conclusion. It's still compatible with prediction of self-organized criticality.
Okay, so basically you're saying even if you make it a bit more complex, the method
if you use another model of gamma ray burst, you use another pulse model, probably it will not change the conclusions, but maybe it will change a bit the parameters.
Okay. Okay. Thanks. Thanks a lot.
Other questions, please? Yes, somebody. Yeah, Dmitry, please.
Hello, I'm Dmitry Svinkin from Cornerstone team. Thank you for a very interesting talk. And I have a small question on the slide 18, I think, where you calculating the energy in a single pulse.
Yes.
So you mentioned that you take a time integrated spectrum, then calculated the ratio of counts in a pulse and in a whole burst. And this way you calculate the energy in a single pulse. But there is for example, hardness intensity correlation in a gamma ray burst. So the spectrum in different pulses can be different.
Yeah, so the spectrum can be evolving, so it will be more correct to do a time resolve analysis. Actually, in the appendix of the paper, you can see we performed also this kind of analysis, but only on a few bursts, because it would be maybe too difficult to do it on a sample of 100 of bursts. So we check it for few bursts. We check that if we performed time resolve analysis instead of time average, it doesn't affect too much the results.
Thank you.
You're welcome.
Thank you.
Other questions, please? No questions. Then I have a question. So Romain, when modeling the isotropic energy release distribution and the luminosity distribution, you used the broken power law. So I'm wondering whether you considered, for example, a power law with an exponential cutoff, or how did you decide to use the broken power law as a proxy for the luminosity function and the energy release function? Yeah,
it's a broken power, so it's not continuous break. It's like in this plot, the slope is changing at the breakpoint, like that.
Yeah, I see. I mean, the question is essentially, why have you opted for the broken power law, not for a power law with an exponential cutoff, for example?
I mean, we did not test this model, I guess. The choice, maybe we could have also tested other models, but this one was already giving a good description of the data.
Actually, there was a paper led by Jean-Luc Atteya in 2017, and he studied the energy release function, the distribution of energy releases, and he applied several models to fit this function, and figured out that for the isotropic energy release, maybe the power law with exponential cutoff is a better option than the broken power law. Also in two catalogs in 2017, 2021, 2021, 2017, we also constructed the energy release, the isotropic energy release and isotropic luminosity functions, and we figured out that the luminosity function is better fitted with the broken power law, and the energy release function is, according to our data, was better fit with the power law, the exponential cutoff, which might be a hint on the maximum energy release or something like this. So basically, that was my question. Thank you very much. Other questions, please? Okay, if there are no questions, thank you very much again. The talk was really interesting. Thanks a lot. Looking forward from hearing from you.